On December 27, 2004, an invisible wave of energy slammed into Earth. It hit with enough force to physically expand our planet's upper atmosphere, altering the ionosphere in a fraction of a second. In just 0.2 of a second, this burst delivered more energy than our sun will produce over the next 150,000 years. But this blast didn't come from a supermassive black hole or a dying star going supernova. It originated from an object only 12 miles across, sitting 50,000 light-years away. A tiny sphere designated SGR 180620. This object is a magnetar. It is a rare cosmic anomaly that wields the most powerful magnetic forces in the known universe. When massive stars die, they often leave behind neutron stars, crushed cores so dense that a single teaspoon of their matter weighs 1 billion tons. But about 1 in every 10 of these stellar corpses mutates into something far more dangerous. This animation shows the Taylor-Sprout dynamo. During collapse, the stellar core spins up to 1,000 times a second as internal material violently boils. This twisting supercharges the star. The magnetic field erupts outward, reaching 10 to the 15th Gauss, a quadrillion times stronger than Earth's. To truly comprehend a force this extreme, we have to take a hypothetical one-way journey straight toward a magnetar to see what happens to matter, light, and the human body. Crossing the 100,000-mile mark, the effects are immediate. From this distance, the magnetic field is already intense enough to instantly wipe clean every credit card, hard drive, and digital satellite system on an approaching spacecraft. Looking at this diagram, we see the magnetar's extreme gravity warping the surrounding space. Light rays originating from the far side are pulled completely around its mass, allowing an observer to see the back of the star while looking directly at the front. But gravity isn't the only thing altering the view. The magnetic field actually magnetizes the vacuum of space itself, a phenomenon called birefringence. This field acts like a prism, fracturing and polarizing the light rays as they pass through. At this distance, silicon and magnetic storage simply cease to function, and the vacuum of space itself begins to behave like a solid lens. Pushing forward to the 1,000-kilometer mark, human survival shifts from highly dangerous to biologically and atomically impossible. This graphic shows exactly what happens to a standard atom at this proximity. The magnetar's field overpowers the very forces holding atomic structures together. The electron clouds are violently stretched along the magnetic axis, turning spherical atoms into microscopic needles 100 times longer than they are wide. The macroscopic consequence of this atomic stretching is absolute. If a human were standing here, their body would instantaneously dissolve into the void as its chemical bonds snapped. Flesh and bone simply cannot exist in this environment. To reach the surface, we have to rely on an indestructible hypothetical probe to carry us the rest of the way. Touching down on the surface reveals a desolate environment. The crust is an unimaginably dense iron lattice, heated to 5 million degrees. Beneath our feet, immense internal tension is building. The super-strong magnetic fields inside the star are tightly wound up, constantly pushing, twisting, and straining against this brittle outer shell. This data slide shows the parameters of what happens when that crust finally snaps. A starquake triggers a violent rearrangement of the magnetic field, blasting out fast radio bursts and gamma rays. Looking at the formulas, we see the sheer energy output generated by this model, reaching roughly 10 to the 39th ergs of energy. A microscopic fracture on a crust barely 12 miles wide is all it takes to cause an apocalyptic burst of energy capable of shaking Earth's atmosphere from 50,000 light-years away. Plunging below the crust, the extreme gravity and magnetism rip atomic nuclei apart entirely. The material here turns into a dense fluid sea of pure neutrons. This cross-section illustrates how the structure of that dense matter changes as we sink deeper. The pressure forces the neutrons into bizarre geometric phases, first clumping into spherical drops called nuclear gnocchi, then stretching into long vertical strings known as nuclear spaghetti, and finally flattening into parallel sheets of nuclear lasagna. Reaching the absolute center, these distinct shapes dissolve. The core is a uniform superconducting fluid, likely composed entirely of strange matter. This exotic interior represents the absolute physical limit of matter. Adding any more mass or pressure would cause the entire structure to collapse inward, forming a black hole. Given the sheer destructive power of these objects, you might wonder why they haven't completely sterilized our galaxy. The answer lies in a built-in braking mechanism. The Magnetar's massive magnetic field expels so much momentum into space that it acts as a physical brake, violently dragging against the star's rotation. Within just 10,000 years, a blink of an eye in cosmic time, the Magnetar exhausts its spin power and drains the vast majority of its energy. A Magnetar's greatest weapon, its world-ending magnetic field, is ultimately the exact mechanism that guarantees its own rapid death. Looking at our current galactic map, astronomers have only identified about 34 active Magnetars. Fortunately, the closest one sits safely 9,000 light-years away from Earth. But because they burn out so quickly, there is a chilling reality to consider. There are likely hundreds of thousands of dead Magnetars drifting silently and undetected through the Milky Way right now. Magnetars represent the absolute edge of observable physics, fleeting, hyper-violent anomalies that briefly hurl the universe's most extreme forces out into the galaxy before returning to silence.